team members. Closest to me is Lucas Monson. Then I got Jade Kim, Sophia An, and Usama Ali. And together we worked on the pulse current source for electrostatic discharge for Texas Instruments. So in integrated circuits, there's a huge problem of electrostatic discharges. It leads to failures in the ICs. So our idea here was to design a system that was portable, that can move around, and that could actually connect to these ICs, and we could test them to see what their failures are. So starting out on this project, we had to, there was a previous team that did it last year, and we needed to improve what they did. So their output pulse was about 30 volts at about a half an amp, and had a rise time of about 20 nanoseconds. So where we wanted to get to was at least 120 volts or more, and we wanted at least 1 amp, and a rise time of less than 10 nanoseconds, and a pulse width that could vary from 2 to 2,000 nanoseconds. This is closely represents the human body model, which is what we're trying to get to so we can test these devices sufficiently. So in our simulation, what we've designed at this point is our circuit down here below. And kind of how it works is we have some multi-vibrators that actually generate a pulse. It's a periodic pulse. That pulse will actually get sent through a MOSFET driver along with an analog switch at high speed. That will create a low voltage, high speed, very fast on the rise time pulse. That pulse then is sent through this MOSFET driver up here, which is a high speed, high voltage MOSFET. This is the one that's going to basically amplify our signal. And so far we've achieved 120 volts. We've had it about 9 nanoseconds or less on the rise time, as you can see here. And basically we want to take this design next semester, implement this onto a breadboard, get it working. Then we'll make a PCB board, design that. Also, the output here we'll send to a ADC board, which will convert it over, and we'll have that interact with LabVIEW. As well as also in the simulation, what we don't have is a DC to DC converter. We had to get a high voltage, around 300 volts, to actually drive this MOSFET to get the output pulse that we wanted. So that was it for the semester. Any questions? Yeah.
How did you do anything special, or how did you pick your MOSFET?
That was what took us the longest time with research. When we finally found one that could do, what'd you say, Lucas, about 300 volts?
Yeah, it maxes out at 250. I don't remember the exact model name, but it's by Infineon. That was, like you said, the most time-consuming part of this whole semester is finding the perfect MOSFET that will suit our needs.
And just out of curiosity, what was the bandwidth of that part? Can you specify, or must have been really fast?
Yeah, it was, the rise time was what, about 9 nanoseconds?
Right.
It's really good.
Yeah. In fact, it's only been out for a couple months now.
Yeah, it just came out this year.
So
Because of that, they don't have any simulation models yet. So we've been actually making the simulations with one that is like the previous model, slightly slower and higher voltage. We went ahead and ordered that part. I'm pretty confident that is what we're looking for. And as soon as it arrives,
You measure it with a regular scope, or?
yeah, just oscilloscope. It has to be high speed,
Yeah.
high voltage oscilloscope, and we have to get a special one, basically to measure the signal on this. Do you have a question?
Is this all simulation you?
Yes. This is, everything we did was an LT splice at this point. We've gotten all the parts, and we're going to start testing everything, and then like I said, we'll start assembling this before we look to solder this onto a PCB board. And basically we'll make a custom box. Like I said, it's portable, so it's going to run off of one battery. And then basically, like I said, then the idea too is also just USB, and we can connect it to the computer, so we can actually view the pulse, and we can have some controllability of the pulse width, the frequency of the period of that pulse, as long as with the high voltage we can control all that.
Have you, at this stage, have you considered the PCB characteristics and what's going to impact that 90 nanoseconds?
Yes, there is going to be some delay to that. That's why we did exhaustive time looking at it. So there is going to be some delay. I don't think it might add up to some. That's one of the things we're going to have to test to see, basically. There will be some delay on the breadboard as well, the way that is with PCB along those.
Well, not really. There's some delay there, but that rise time may
Yeah, because what we're using right now is just the load for the resistor, and obviously that will change based on the output. Basically, like I said, it's going to be measured and it's going to be converted. So the other thing is it has to have, it'll have a direct connect, and it's based on the load on that integrated circuit that you put out to. That's the barrier to, and those are things that we have to test.
On the modeling, were you able to get, with the exception of the loss that, were you able to get all the price models?
Yeah, well, the other thing we weren't able to do was the DC to DC converter. We couldn't find a spice model that we emailed the company and they said we didn't have one. That was, we found ones that were around 100, but not as high as the DC to DC converters at 300 volts. So basically, we just made in the simulation, just made a voltage source that was 200 volts to drive that MOSFET. So,
On your power supply, I guess on this, if you didn't have a capacitor, even is it going to be controlled power, or you probably should have been informed about?
right.
You just, it's a pulse for the low duty cycle.
Oh, let me see what I'm trying to understand what you're saying. For the power supply, for the drive that MOSFET, is that what you're referring to?
Right, we use that.
Yeah, we have it, we already ordered